Hello everyone, welcome back to my YouTube channel. In this session, I am going to explain about the types of solar cell material, which is the topic of renewable energy sources. The solar cell material. The basic component of a solar cell is pure silicon, which has been used as an electrical component for decades. Silicon solar panels are often referred to as first generation panels, as the silicon solar cell technology gained ground already in the 1950s. Currently, over 90% of the current solar cell market is based on silicon. Pure crystalline silicon is a poor conductor of electricity as it is a semiconductor material at its core. To address this issue, the silicon in a solar cell has impurities, meaning that other atoms are purposefully mixed in with the silicon atom in order to improve silicon's ability to capture the sun's energy and convert it into electricity. There are types of silicon used in solar cell. They are: the first type is amorphous silicon. This amorphous silicon, it is called as ASI, is the non-crystalline form of silicon used for solar cells and thin film transistors in LCDs. It is used as semiconductor material for thin film silicon solar cells. It is deposited in thin films onto a variety of flexible substrates such as glass, metal, and plastic. Amorphous silicon cells generally feature low efficiency. As a second generation thin film solar cell technology, amorphous silicon was once expected to become a major contributor in the fast growing worldwide photovoltaic market, but has since lost its significance due to strong competition from conventional crystalline silicon cells and other thin film technologies such as CDTE. The amorphous silicon is preferred material for the thin film transistors, that is TFT elements of liquid crystal displays LCDs, and for the X-ray images. The applications of amorphous silicon are: one further advantage is that ASI, that is amorphous silicon, can be deposited at very low temperatures, example as low as 75 degrees Celsius. This allows deposition on not only glass but on plastic or even on paper substrates as well, making it a candidate for a roll-to-roll processing technique. Once deposited, ASI can be doped in a fashion similar to CSI to form P-type or N-type layers and ultimately to form electronic devices. Another advantage is that ASI can be deposited over large areas by PECVD. The design of PECVD system has great impact on the production cost of such panel. Therefore, most equipment suppliers put their focus on the design of PECVD for higher throughput that leads to lower manufacturing cost. The next one is polycrystalline silicon. The polycrystalline silicon or multicrystalline silicon, also called polysilicon or poly-Si, is a high purity polycrystalline form of silicon used as a raw material by the solar, photovoltaic and electronics industry. Polysilicon is produced from metallurgical grade silicon by a chemical purification process called the Siemens process. This process involves distillation of volatile silicon compounds and their decomposition into silicon at higher temperatures. An emerging alternative process of refinement used as fluidized bed reactor. The photovoltaic industry also produces upgraded metallurgical grade silicon, that is UMGSI, using metallurgical instead of chemical purification processes. When produced for the electronics industry, polysilicon contains impurity levels of less than 1 part per billion, that is 1 ppb, while polycrystalline solar grade silicon is generally less pure. The polysilicon manufacturing market is growing rapidly. According to Digitimes, in July 2011, the total polysilicon production in 2010 was 209,000 tons. First tier suppliers account for 64% of the market, while China-based polysilicon firms have 30% of market share. The total production is likely to increase 37.4% to 281 tons by the end of 2011. For 2012, EE Times Asia predicts 328,000 tons production with only 196,000 tons of demand, with spot prices expected to fall 56%. While good for renewable energy prospects, the subsequent drop in price could be brutal for manufacturers. As of late 2012, Solar Industry Mag reports a capacity of 385,000 tons will be reached by year end. The next one is monocrystalline silicon. It is often called single crystal silicon, in short mono-Si, is the base material for silicon-based discrete components and integrated circuits used in virtually all modern electronic equipment. Mono-Si also serves as a photovoltaic light-absorbing material in the manufacture of solar cells. It consists of silicon in which the crystal lattice of the entire solid is continuous, unbroken to its edges and free of any grain boundaries. Mono-Si can be prepared as an intrinsic semiconductor that consists only of exceeding pure silicon, or it can be doped by the addition of other elements such as boron or phosphorus to make p-type or n-type silicon. Due to its semiconducting properties, single crystal silicon is perhaps the most important technological material of the last few decades, the silicon era, because its availability at an affordable cost has been essential for the development of the electronic devices on which the present day electronics and IT revolution is based. The monocrystalline silicon is also used for high-performance photovoltaic devices. Since there are less stringent demands on structural imperfections compared to microelectronic applications, lower quality solar-grade silicon, that is SOG-SI, is often used for solar cells. Despite this, the monocrystalline silicon photovoltaic industry has been benefited greatly from the development of faster mono-Si production methods for the electronics industry. The below diagram shows the monocrystalline, polycrystalline and amorphous silicons. In the monocrystalline silicon, the atoms are arranged compactly. In the polycrystalline silicon, the atoms are liberally arranged, but in amorphous silicon it is more liberally arranged compared to other two crystalline silicons. The next one is thin film solar cells. These are made by depositing one or more thin layers of photovoltaic material onto a substrate such as glass, plastic or metal. Thin film solar cells are typically a few nanometers to a few microns thick, much thinner than the wafers used in conventional crystalline silicon, that is CSI based solar cells, which can be up to 200 microns thick. Thin film solar cells are commercially used in several technologies including cadmium telluride, that is CDTE, copper indium gallium diselenide, that is CIGS, and amorphous thin film silicon, that is ASI and TFSI. Solar cells are often classified into so-called generations based on the active layers used to produce them, with the most well-established or first-generation solar cells being made of single or multicrystalline silicon. This is the dominant technology currently used in most solar PV systems. Most thin film solar cells are classified as second generation, made using thin layers of well-studied materials like amorphous silicon, cadmium telluride, copper indium gallium selenide or gallium arsenide. The solar cells made with newer, less established materials are classified as third generation or emerging solar cells. This includes some innovative thin film technologies such as perovskite, dye-sensitized quantum dot, organic and CZTS thin film solar cells. Thin film cells have several advantages over first generation silicon solar cells, including being lighter and more flexible due to their thin construction. The figures showing below are examples of thin film solar cells. A thin, in a thin film solar cell, the process is largely the same, but the active semiconducting layer is made much thinner. This may be made possible by some intrinsic property of the semiconducting material used that allow it to convert a particularly large number of photons per thickness. For example, some thin materials having a direct band gap, meaning the conduction and valence band electron states are at the same momentum instead of different momenta, as in the case of an indirect band gap semiconductor like silicon. Having a direct band gap eliminates the need for a source or sink of momentum, simplifying the two-step process of absorbing a photon into a single-step process. Other thin film materials may be able to absorb more photons per thickness simply due to having an energy band gap that is well matched to the peak energy of the solar spectrum. That's all for this session. Thank you.